steric number determines the shape, the geometry, the molecular geometry. Steric number is actually the total number of bond pairs and lone pairs in the outermost shell of the central atom, and this determines the shape of molecules. For you to know the bond pairs and lone pairs, sum them together, you'll be able to know the steric number, and for you to know the steric number, you can predict the shape. There is established fact about the shape of a molecule and the steric number. But one should be careful here, because steric number do not just mean the total. I might have 4 as my steric number, you have 4 as your steric number, but we have different shapes. What matters is what makes up that my 4. How many lone pairs are involved in that 4? How many bond pairs are involved in my 4? If I have 4 bond pairs and 0 lone pair, I have a different shape. If you have 3 lone pairs and if you have 3 bond pairs and 1 lone pair, total steric number is still 4, but you have a quite different shape from the one that have 0 lone pair. So it depends on the constituents of the total steric number. So we go first by identifying which one is lone pair and which one is bond pair. I'm going to use 3 molecules, which are, I'm going to use water, I'm going to use ammonia, and I'm going to use methane. From there, we will now know what you mean by bond pair, lone pair. Okay. Okay, right here we see these shapes. Let's determine their steric numbers. We start with methane. Remember, if you are determining the steric number, you will also know the designations of the lone pairs and bond pairs. So here is methane, which has how many lone pairs? 0 lone pair, but bond pair are 1, 2, 3, and 4. So there are 4 bond pairs here, meaning those electrons that were contributed is what we call contributed by different atoms. That's what makes up the bond pair. The cross here is to represent the one from hydrogen, while the dot represents the one from carbon. You can use cross for carbon and dot for hydrogen. So this is what we call the cross and dot diagram, just to know the contributions. So they are all paired. One came here, so contributed pairs are what we call the bond pairs in a covalent molecule. So the steric number here is 4. But what makes it up? 4 bond pairs and what? 0 lone pairs. Then when you come here also, we have how many bond pairs? 1, 2, 3. We have 3 bond pairs with 1 lone pair. This lone pair is the one that is not contributed. It belongs solely to the nitrogen. So this nitrogen automatically has this pair here, and it's called lone pair. It's not participating. It wasn't contributed by 2 atoms. It's only belonging to nitrogen and is a pair. But this one here is a bond pair because 1 electron here came from nitrogen, the other came from hydrogen, and they bonded together. So this one has 3 bond pairs plus 1 lone pair, which gives us 4 as the steric number. So methane and ammonia have the same steric number, but the constituent is not the same. Methane has 4 bond pairs and 0 lone pair, while ammonia has 3 bond pairs and 1 lone pair, which will affect the shape. Then this structure here is actually water molecule, which has how many lone pairs? It has 2 lone pairs, 1, 2, plus 2 bond pairs, which is 4. So these molecules here all have 4 as their steric number. Does it mean that the steric number must be 4? No. Steric number can start from 2. Can be 3, 4, 5, 6. I'll give you examples, but I'm using this for you to understand what we mean by steric number. Now, having understood the steric number, we want to use it now to determine shape. This is a generalized fact. When the steric number of a given molecule is 4, which is made up of 4 bonds and 4 bond pairs and 0 lone pair, the shape is tetrahedral, and that is observed in sp3 hybridized molecules. So this shape, this methane, is automatically tetrahedral. Ethane is also tetrahedral because the central atom will have the steric number of 4 bond pairs and 0 lone pair. But in ammonia, we have 3 bond pairs and 1 lone pair. If this occurs, if the steric number is 4, which is composed of 3 bond pairs and 1 lone pair, the shape of that molecule is nothing but trigonal pyramidal. So trigonal pyramidal is the shape of this ammonia. This is applicable to any other molecule you will meet. If you have 3 bond pairs and 1 lone pair, the shape must be trigonal pyramidal, and the bond angle automatically is 107 degrees. But the bond angle here is 109.5 degrees. Then if you come to water, water also have 4 as the steric number, but it has 2 lone pairs and 2 bond pairs. If you see any molecule with 2 lone pairs and 2 bond pairs, the shape is V shape or bent or angular, and the bond angle for water is 104.5 degrees. So this is it for the steric number and the possible shapes. You can see the table where these facts are all listed. Okay, we can have other steric number that is not exactly 4. Let's take a look at molecules that have 2 as their steric number, like carbon 4 oxide has the steric number of 2. And then let's see what happens there. In counting steric number, double bonds are counted as 1. It's only single bonds that are counted. See what I mean? If I have such structure like this, if I want to count this, how many is the, look at the central atoms. Is it bonded to how many other atoms around? This carbon is bonded to 1, 2, 3. So the steric number of each carbon here is 3. Even this one is 3 also. So in this case, if you want to count the bonds, don't count this 1, 2, 3, 4. No, double bonds are counted as 1 because pi bonds are not counted. Even triple bond, you take it as 1 because it's only the sigma bonds that are counted. Out of these 2 bonds, 1 is sigma and 1 is pi. If you have 3 bonds, there will be only 1 sigma bond. So only 1 sigma bond can exist between one carbon and the other carbon. Therefore, that's why we count only 1. So the steric number here is only 3. How many lone pairs? 0 lone pair. So if you have 3 bond pairs and 0 lone pair, the shape is still trigonal, but it's going to be trigonal planar. But when you have 3 bond pairs and 1 lone pair, it becomes trigonal pyramidal. But when you have 3 bond pairs with 0 lone pair, it becomes trigonal planar. So alkenes, that's one with the double bond, like ethene should be trigonal planar in shape. You get that gist now? Boron fluoride should also be trigonal planar in shape because there is no lone pair, but rather 3 bond pairs all through. Then coming to this, what's the steric number of carbon 4 oxide? Is automatically 2 because the total number of atoms surrounding the central atom is 1, 2, or you can count the bonds, which means I told you if you see double, count it as 1, 1, 2. So the steric number is 2, and there is no lone pair. So when we have 2 bond pairs with 0 lone pair, the shape is automatically linear, and the bond angle in linear shaped molecules is 180 degrees. Lest I forget, the bond angle in trigonal planar shaped molecules is 120 degrees. But in trigonal pyramidal is 107, is less than that of trigonal planar. I will explain that under the valence shell electron pair repulsion theory. Why do we have trigonal planar and trigonal pyramidal? Is the theory that will explain such possible shapes.
Wait a minute, have you heard about the majestic table? It was designed and recommended by Her Majesty himself. Here it is. The amazing thing about the majestic periodic table is that it provides a clear and colorful classification of elements, from P block metals to metalloids to liquid metals. It also shows the boiling and melting points of all the elements. It also has the unique feeling of electrons in the shells of each element.